We have finished discussions on ungrounded system, solidly grounded system, and high-resistance grounded system. Next, we will take up low-resistance grounded system. Any one of the following criteria is used when designing low-resistance grounded system. The ground fault current IF is limited to 200 to 500 amps. This criterion is very widely used. Or, in some cases, the following criteria is used. Ground fault current IF is limited to some percentage, say 50%, of rated current of source transformer or generator. For example, consider 10 MVA transformer. At 6.6 kV, rated current IR is 875 amps. The resistance R in neutral is sized to limit ground fault current IF to 50% of IR, that is 0.5 into 875 equals 438 amps. Low-resistance grounding is widely adopted in MV systems, that is 3.3 kV, 6.6 kV and 11 kV, where rotating machines like motors and small generators are present. This is a compromise between high-resistance grounded system and solidly grounded system. Compared to high-resistance grounded system, the core damage at the faulted location will be more, but the machine sizes are much smaller, generally in the range of 1 to 10 megawatts. The ground fault current is neither too high in kiloamps, as in the case of solidly grounded system, nor it is too low, that is, less than 15 amps, as in the case of high-resistance grounded system. Since sufficient ground fault current is present, current-based protection using CBCT is widely used for both detection and isolation of faulted feeder. The design of resistor is illustrated with an example. Consider a 11 kV machine. The ground fault current, IF, is to be limited to 400 amps. Value of resistor RG to be connected in neutral equals V phase by IF equals 11 kV by root 3 divided by 400 equals 16 ohms. The value of resistor is small. The resistor can be directly connected between neutral and ground, as shown in the figure. For comparison, in case of high-resistance grounded system, value of resistor was 635 ohms, as shown in bottom figure on right. In this case, we used NGT and connected the resistor across NGT secondary. Since the ground fault current is limited to within 400 amps, heat dissipation, I2R loss, is not excessive, and enclosures can be designed economically, so that temperature rise is within limits. Mounting arrangement of neutral grounding resistor is shown in the picture. The enclosure with louvers is mounted on a pedestal, approximately 2.5 meters above ground, so that it is not approachable easily. The other point to note is that the enclosure is mounted on insulator, so that the resistor element within enclosure is electrically isolated from support structure. Typical dimension of enclosure is 700 by 700 by 1500 millimeters. The enclosure is compact, since it is designed only for 10-second duty. In practice, ground faults are cleared within 1 second. In earthing module, topic of NGR enclosure earthing was discussed. Just for continuity, we are repeating the discussions here. The resistor stacks are made of stainless steel or cast iron grid. NGR enclosure rests on support insulators. Unlike other electrical panels, NGR enclosure should not be earthed. The reason for the same will be explained in next slide. Since the panel is not earthed like conventional panels, it is mounted on a pedestal to minimize the chance of human contact with panel body. We will summarize our observations. When all insulator stacks of NGR are healthy, the flow of fault current back to source is as shown. Assume now insulator X has cracked. Under this condition, the flow of fault current back to source is as shown. It is same as previous case. Assume now the enclosure is earthed. It is shown as connection E1F. Under this condition, the flow of fault current back to source is as shown. The resistor is completely bypassed. What is intended to be resistance-grounded system has become solidly grounded system. If a ground fault occurs, ground fault current will be in kiloamps and not 100 to 400 amps. A simple mistake of panel earthing can be disastrous.